So we're going to continue on with enzymes. And oh, by the way, I noticed that in my previous video when I was telling you guys about the classes of enzyme, I actually wrote classes with one S. How ridiculous. I apologize. So obviously I should have done that. Okay, so continuing on. Now we know the terminology. An active site is where the substrate binds. The active site is a bunch of amino acids in a specific location of the enzyme where the actual catalysis or the reaction takes place. An enzyme that is called a simple enzyme is an enzyme that doesn't have a prosthetic group. A conjugated enzyme has a prosthetic group, which is a non-protein portion. So a conjugated enzyme has a protein and a prosthetic group. That prosthetic group is called a cofactor, and there are two types of cofactors. There's the organic kind and the inorganic kind. Let's start off with the inorganic cofactors, and those are typically things like magnesium and zinc, magnesium ion, and zinc. They are very important inorganic cofactors for many enzymes in the body, hundreds of enzymes in the body. The enzyme I worked on in my research was tyrosine kinase. Remember how I told you guys that a kinase transfers a phosphate group? Well, tyrosine kinase transfers a phosphate group onto tyrosine. And magnesium was a very important cofactor for that enzyme that I worked on. And if you don't put magnesium, the enzyme is an apoenzyme and it just does not work. Okay, so these are examples of inorganic cofactors. The organic cofactors are sometimes called coenzymes. We call them organic coenzymes, and they are usually derived from the B vitamins. If you've had a nutrition class, you know that there are water-soluble vitamins and fat-soluble vitamins. A, D, E, and K are the fat-soluble vitamins. B and C are the water-soluble. Okay, you're going to see the uses for a bunch of these vitamins throughout the semester, but let's now focus on the B vitamins. The B vitamins, many of them are used to create organic coenzymes. Niacin, which is vitamin B3, is used to make NAD. NAD is called nicotinamide adenine dinucleotide. This is a coenzyme that you will see with a bunch of the dehydrogenase enzymes. Riboflavin. Riboflavin is vitamin B2, and that makes the coenzyme FAD. FAD is flavin adenine dinucleotide, and that also is used in a few of the dehydrogenase enzymes. So basically, if you don't have that coenzyme there, the enzyme doesn't function, okay? And these are derived from these B vitamins. Pantothenic acid, this is B5. It is used to make coenzyme A. Coenzyme A, pantothenic acid, is one of the B vitamins. Coenzyme A, we're going to see that in acetyl-CoA goes into the Krebs cycle. So when you're done with glycolysis and you do like this transition reaction between glycolysis and Krebs, you turn pyruvate into acetyl-CoA. Anyway, the CoA portion of acetyl-CoA is this coenzyme A, very important coenzyme to carry the acetyl group into the Krebs cycle. There is thiamine, which is vitamin B1. That is important in creating the coenzyme TPP, which is thiamine pyrophosphate. What else? Oh, there's pyridoxine or pyridoxal, which is B6. It is important in making a coenzyme called pyridoxine phosphate, pyridoxal phosphate, anyway, PLP. The idea is that the B vitamins are used to make coenzymes that will then be prosthetic groups, organic prosthetic groups to help enzymes do their thing. Let me see if there's another one that I'm missing. I feel that there's another one I'm missing, but these are the most important ones for now, so we can move on. All right, let's go ahead and talk about the different models for enzyme action. The lock and key model is absolute specificity, meaning the enzyme is very rigid and the substrate has to fit directly into a proper place. Lock and key. Key words here is absolute specificity. So the enzyme in the lock and key model is a rigid enzyme. It does not move. There's no moving around. The substrate has to fit in perfectly, just like a key into a lock. I don't know how many of you guys have ever made a copy of a key. And sometimes when you make a copy of a key and you put the copy into the lock, it won't work. And only the original key will work. That's the lock and key model. Very, very rigid, very specific, end of discussion. The one that is more flexible is the induced fit model. Induced fit. And I think this is the one that is used most. And as you read through your chapter, you get the idea. But basically, this says that the active site kind of accommodates the substrate. Now, active sites are very substrate specific. So if, for example, you have a sucrase enzyme, only sucrose is going to fit there, but the enzyme moves a little bit to allow the sucrose to fit in. It does not mean that it's going to move and allow a lactose to fit in, okay? So we are very substrate specific, but not super rigid. So there's a little bit of movement here. That's the induced fit. So people with a lactose intolerance, for example, the lactase enzyme is lacking and they can't use sucrase enzyme to catalyze the hydrolysis of lactose, all right? It's not that flexible. It's just that the enzymes move around a little bit, okay? Now, how are we going to affect the enzyme activity? There are several factors that affect enzyme activity: pH, temperature, concentration of the substrate, concentration of the enzyme. All right, so let's first talk about pH. Now think about the enzymes in your body. If you've got an enzyme working in your mouth, it's going to be different than the enzyme working in your stomach, because you know that the pH of the stomach is very low. It's a very acidic environment. So there's always an optimum pH for each enzyme for whatever environment it's working in. So all the digestive enzymes that are in the stomach have an optimum pH of 1. It's a funny sound, of somewhere in the 1 range, in the very acidic range. The enzymes that are working in the bloodstream or in the intestines or in the mouth, their optimum pH is going to be the pH of the mouth or pH of the intestines or pH of the blood, okay? So here's pH, here's enzyme activity, and this is the optimum pH. This optimum pH varies depending on where it is in the body. Okay, like I said, pepsin, for example, that works in the stomach, its optimum pH would be 1. the enzyme maltase. It works in the small intestine. Small intestine is a little over 7, so its optimum pH would be around 7ish or a little higher. Okay, temperature. What do you think? Well, very cold temperature, probably enzymes don't work very much. They're very slow. Very high temperature, the enzyme could get denatured. So ideally, if it's in the body, what do you think the ideal temperature would be for an enzyme in the body? Probably body temperature. Normal body temperature is 37 degrees Celsius. That's probably the ideal temperature for that. So normally with a temperature diagram and enzyme activity, what we'll see is you get, and this is enzyme activity, low temperature, not much activity. You get a nice optimum temperature, and then as you're increasing the temperature, it's going to go down again. So this would be the optimum temperature. And for enzymes that work in humans, usually the optimum temperature is going to be 37 degrees Celsius. So if in lab you take an enzyme and you boil it, you're going to denature it. It's a protein. It's not going to be active. Or if you take, and so it won't do much of anything. If you take an enzyme and stick it in an ice bath, it's going to be really slowed down. So temperature this way, low temperature, high temperature, optimum temperature. Okay, substrate concentration. As you increase the substrate concentration, the activity of the enzyme will go up. So we're going to write substrate concentration goes this way, and enzyme activity goes up, is this way. All right, y-axis enzyme activity, substrate, x-axis. All right, so as you increase the substrate concentration, enzyme activity goes up. As you increase, enzyme activity goes up. And then it starts to do this. Why do you think it's plateauing like this? Well, this has to do with the enzyme active sites. So if you keep increasing the substrate, great, but you've filled all the enzyme active sites, so now we're just stabilizing for activity. You got to empty out all those enzyme active sites, produce all the product, and then you can have more activity. All right, so this is the typical graph for substrate versus enzyme activity. And then the last one is enzyme activity versus enzyme concentration. So here we're assuming we have an unlimited supply of substrate, and we're just focusing on adding enzyme. So you're adding enzyme, activity goes up. You have plenty of substrate. Adding enzyme, activity goes up. Adding enzyme, activity goes up. And this just keeps on going. Okay, it's not going to plateau here because you've got plenty of enzyme, you've got plenty of substrate. You're just going to keep having enzyme activity. All right. So that does it for things that affect enzyme activity. The next video, we will talk about inhibition of enzymes.